In this brief video, we want to talk about different kinds of modulation schemes used in radio. We'll look at radio bands and those modulation schemes, and then in the future videos in this module, we'll look at VOR, DME, and ILS. So radio happens because electromagnetic waves propagate, and it's being able to change things like the amplitude and frequency of those propagating waves that gives us the ability to put information into radio signals. Basically, when you have an alternating electric field, it generates a magnetic field. When you have an alternating magnetic field, it generates an electric field. So if you have mutually alternating electric and magnetic fields, you get a propagating wave, an electromagnetic wave, a radio wave, if you will. And that's formally described by Maxwell's equation, which you may or may not have seen in some form in your physics class. The electromagnetic spectrum then is the complete set of all the different frequencies, and of course the lower the frequency, the longer the wavelength, the higher the frequency, the shorter the wavelength. So some radio spectrum bands are referred to by their wavelength, and some are referred to their frequency. We're going to talk frequencies here, although again in certain usage like amateur radio ham, they often talk about long wave, short wave, and the like. So here's the spectrum of allocated frequencies that are used. You can see, I mean, it's really hard to see things. They talk about an eye chart. This is really an eye chart. You should download the full-size version of this and print it out at like a 4x8 poster or something like that. It's huge. Anyway, the things that are colored in brown here are bands that are used for aeronautical radio navigation. Upper level items are primary, lower ones are secondary, and there may be some tertiary uses of certain frequency bands. So we see navigation stuff starting from fairly low frequencies below 300 kilohertz into the sort of the AM band through here. Again, my eyes aren't good enough to see all these, even as I'm looking at it from here. This is broadcast. I think this is your AM radio band here from 535 to 1605, somewhere around there. Down here are your television bands and the like, but the radio navigation ones are shown in brown. So again, you see these in different frequency ranges, 3 megahertz, 30 megahertz. There's not a lot of radio navigation in that band, but you get back up in here into the 30 megahertz to 300 megahertz. Here's a band here just above the radio spectrum, FM radio. So again, it's all over the place, even higher bands here. So let's look at what some of these bands or basic frequency ranges are and where some of the applications within those are. For low frequency and medium frequency waves, we have the non-directional beacon, and then we also saw that big chunk for commercial AM radio there. Higher frequency is used for long-range communication, and then we get into some more navigations like VOR in the very high frequency. For ultra-high frequency, we have more communications, satellite communications, and the like. When we get into, of course 802.11, 2.3 gigahertz, and the like. Super high frequency is used for radio altimeter, starting to get into the world of radar here, weather radar, Doppler radar. And then extremely high frequency is used for ground radar, meaning we're going to ground to air radar. We're going to, the kind of radar that you see rotating and sending out around, and also the radar used to monitor things moving around on the surface of the airport. So electromagnetic waves can carry information by modulating either the amplitude or the frequency of a signal. We like to think that signals occupy bandwidth. They take up a certain space, and that depends on how much different kinds of signals are within a certain, how many different kinds of frequencies it takes to make up a different signal. So for instance, my voice here probably effectively has a range up to say 3,000 or 4,000 hertz. That's not an electromagnetic wave, it's an acoustic wave. But it has a bandwidth, say, of 3,000 hertz. That's why it's often said that there's a thing in sampling and converting analog continuous waveforms into digital sampled waveforms, that you have to sample a waveform twice as fast as the highest frequency, and digital telephone waveforms are sampled at 8,000 hertz because that's more than twice the 3,000 hertz bandwidth of speech. Data, there's a lot of different ways to format data. We won't really be talking about those in particular here, but they tend to be higher bandwidth than these, but they have amazing data recovery properties. That is, we can transmit data with perfect recovery if we're willing to put enough bandwidth into it. Amplitude modulation was the first modulation scheme that people came up with. I mean, you can think of Morse code as a kind of amplitude modulation where you're either turning things on or turning things off. But it was figured out that you could take the waveform of a signal, so say the waveform of something like my voice, and use that to modulate the amplitude of a constant frequency sinusoid. And in doing so, you get a copy of the spectrum of the signal that's doing the modulating envelope signal here in this image here on the left. That spectrum gets translated to around the carrier frequency, this fast sinusoid here with its amplitude changing. So if we look on a frequency map, the horizontal axis being different frequencies, the carrier frequency being a pure sinusoid is going to show up as a big spike there. That sort of stands for the sinusoid that is the carrier frequency. And then you get copies of that low frequency wave that's modulating it at plus and minus that frequency. So if this is 3,000 hertz and the modulating envelope is 30 hertz, then this would be at 2970 and this, or excuse me, 2970, and this would be at 3030, and this would be at 3,000. So you get a copy of the spectrum, and you get a copy above and a copy below. That means you're putting a lot of power into that carrier wave. And the like, but it was easy to demodulate. You could demodulate. I mean, you can build a demodulator for traditional AM radio using a rusty razor blade and a pen and some cheap. You could probably make a capacitor out of a aluminum foil and a jar, like a Leyden jar kind of thing or something. Anyway, you can really the initial technology of AM made it possible to have broadcast one high-powered transmitter sending amplitude modulated audio information out to millions of people and have cheap receivers at that end. Point-to-point messaging used in things like public safety. Usually you need more bands first of all, and they often use schemes like AM suppressed carrier and what's called single sidebands. So you can put all the power into the message and only use half of those sidebands, but it takes more complicated electronics. So you couldn't mass market those kind of communication schemes back in the day. The alternative to AM that was early developed was angle modulation, and both phase and frequency modulation are pretty much the same thing. It's a matter of whether you're using the signal or its integral to modulate the waveform. Frequency modulation you know of from the traditional AM radio between 88.1 megahertz and 108. I can't remember what the upper frequency is on the FM scale. And you've listened to AM radio and FM radio probably, even if you do most of your listening over the internet these days, and you know that FM gives you better signal-to-noise ratio. You have almost perfect clarity of signal until the signal degrades, and then you have nothing. Whereas in AM, you just gets noisier and noisier as your signal gets crappier and crappier. So you get better signal-to-noise ratio, but it's done through the cost of bandwidth. And so here, the upper panel in this illustration is showing a frequency-modulated carrier you can see where the frequency is changing as the modulation. So here, let's say the modulation amplitude is high, and here the modulation amplitude is low, and here so it's getting lower frequencies for bigger amplitude, higher frequencies for lower amplitude. That could be backwards. You can do it either way. What you end up getting is not only copies of the spectrum. You don't just get copies, you get, for sinusoidal modulation, so using a tone to modulate this carrier frequency, you get copies of that at different amplitudes. and so the bandwidth gets wider. So here you've got a 600 hertz carrier, and it looks like about 180 hertz modulating signal. And so you get another copy out here, 360 hertz away from 600. You get another out here, another 180 in between here. For broader band signals, again, like speech or music, music you'd like to use up to 20 kilohertz. I think in FM radio they use 10 kilohertz of bandwidth. But you have a frequency deviation. How much is this changing? So is this going from 600 hertz to if this is going from 600 hertz, if we were modulating up to a much higher frequency than this and going up to like 1800 hertz, then we would definitely see 1800 hertz, plus and minus here around 600. So you get, that's called Carson's rule, that the bandwidth required is twice the sum of the message bandwidth and the frequency deviation. So even though the signal in an FM radio may be 10 kilohertz wide, the bandwidth given to each channel is 200 kilohertz, and that's using that extra bandwidth what gives you the ability to counteract noise there. So again, we're going to talk more about some different radio navigation approaches, and they're going to use both AM and FM. We're not really going to talk about LoRaN and MLS. You're going to do a little bit of independent research on MLS in the Thursday session, or we'll talk about it in class, or you'll be doing independent research. And LoRaN is what's called a hyperbolic uses hyperbolic curves and intersections. It's been largely deprecated, and yet it has a continuing value, and so we may talk about that a little bit in the future when we talk about GPS, because the way you figure out where you are is about the same.